Hello students, so welcome back to this channel, and in this session of Abhyas series, we are coming up with the fourth lecture on differential analysis of fluid systems. So please type in the chat box, am I audible to all of you? Can you all see the screen clearly? Okay, fine. So let us start this Abhyas fourth lecture, differential analysis of fluid systems. So basically in some books and all, you know this with the other name fluid kinematics actually. Okay, so basically in this differential analysis of fluid systems, we take a small element of the fluid within a flow and we try to analyze that. Okay, so you might have gone through this fluid kinematics chapter many times till now, and of course you might have done some quick analysis on various things all over. Okay, good morning Rohit. So I hope we are good to go. So shall we go ahead? So please type in the chat box. Shall we start the session? So we have previously done 4 sessions, the 3 sessions on this fluid mechanics Abhyas course. The first one on fluid and its properties, second one pressure and its measurement, the third one hydrostatic forces and buoyancy and flotation, where we have seen some good questions of buoyancy and flotation yesterday. So today we are going to start this session on this differential analysis of fluid systems. Clear? So shall we go ahead? Yes? Ready? Good morning Vishal. So let's start this session quickly. So the first question is here. The velocity and density fields in a diffuser are given by U is equal to U naught times e to the power minus 2x by L, and density is equal to rho naught times e to the power minus x by L. Okay, so they are asking you rate of change of density at x is equal to L. So basically, I would like to give you some mathematical touch, because you see from kinematics onwards, or from this analysis, when you start analysis, you need to have certain understanding of calculus actually, because we talk about the rate of changes of various quantities. So we try to talk about the rates. Okay, so there is one very rule in mathematics which is called the chain rule, or sometimes it's also called the total derivative actually. Okay, so if you follow your calculus, you can get this chain rule or a total derivative. So basically this tells you, if let us suppose if a function is depending on 4 variables, for example say x, y, z, t. Why I am taking x, y, z, t? Because in a 3-dimensional space, if you want to spot any point, then at that point the coordinates are given by x, y, z. So if you want to plot any point in space, you need 3 coordinates x, y and z. Similarly, when there is some unsteadiness in the flow, you also have the time coordinate, correct? So at any time, for example at any location, things change with location and also time. For example, I'll give you one small hint actually. Okay, so let us suppose this is some bar, okay, some 2-dimensional plate, for example. Okay, let us suppose this is some 2-dimensional plate, and let us suppose you are supplying heat to this plate, or let us say from this end you are heating this plate, for example. Okay, from this end you are heating this plate. Okay, you are supplying some heat. So whenever you are supplying some heat, try to tell me this. Let us suppose to analyze this plate, I have taken this as x-axis and I have taken this as y-axis, for example, x, y. Now tell me one thing, when I start heating of this plate, if you take temperatures at these 2 locations, will the temperature be same? Please tell me. If you take 2 points on a horizontal plane, then please tell me, is the temperature at these 2 locations 1 and 2, which are actually on the same horizontal plane, for example, okay, on the same horizontal plane, will they be same? As soon as I start heating, if I measure temperatures after some 5 to 10 seconds of time, then please tell me, will the temperatures at these 2 locations same? Yes, so please tell me. No, correct? It won't be. Yes, obviously it's not same, correct? Because we know depending on the heat transfer, the temperature is different. Similar means you can tell one thing, if I talk about temperature depends on x. You know this because these 2 points are being separated by x dimension. Next, let us suppose if I take one more 2 points, first point, and let us say this is point number 3, for example, then tell me, is the temperature between these 2 points same? Tell me, is the temperature between these 2 points same here? No, obviously. Good morning Abhimanyu. So please type in the chat box, is the temperature between these 2 points same as I start heating? Tell me, it won't be equal, correct? So study material kab launch hoga? Hopefully within very quick time, okay, in this week. Okay, so no, correct? So if you see, this temperature also depends on these coordinates. Why? Because these 2 points are being separated by y coordinate, so obviously the temperature depends upon y. And also there is one very important thing. Let us suppose at the same point t, if I measure the temperature at time t is equal to 10 seconds and at t is equal to 15 seconds, then will the temperature be same at this location in these 2 time periods? Tell me, I have measured the temperature after starting off heating after 10 seconds and after 15 seconds. At the same location, will the temperature change? Means will the temperature be equal at these two times? No, correct? So which means you can observe this also depends upon T. So that's how physically some quantities like pressure, velocity, temperature, these things change from location and from point to point and also with respect to time. So when you go for a 3D analysis in general, the temperature means or the any function in general, any scalar point function or vector point function, if this changes with respect to x, y, z and t, we calculate the derivative of this. Means if there is some function like this, then df, the derivative of this function, is calculated as dou f by dou x into dx plus dou f by dou y into dy plus dou f by dou z into dz plus dou f by dou t into dt. This is called the chain rule of differentiation. Okay, this is one very important concept in mathematics. This chain rule of differentiation gives you the total change of quantity. So you know basically what is this dou f by dou x? This dou f by dou x is nothing but the change of this function in x direction. Similarly, this dou f by dou y is the change of this function in the y direction. Similarly, in the z directions, and also change of f with respect to time. So this is actually the chain rule of differentiation, which you might have seen in calculus, which is one very important thing. Okay, now coming back to our case. What they are asking you is, they have given this velocity profile and also this density profile. They are asking you rate of change of density at x is equal to L. So how will you calculate this rate of change of density at x is equal to L? Just a second, let me take one more slide. So you know one thing, this density is depending upon x and also time, correct? Because you have seen in this density there is involvement of x actually, and of course rate of change of density is nothing but d rho by dt. Okay, so d rho by dt is nothing but d rho by dt is equal to dou rho by dou x into dx by dt plus dou rho by dou t into dt by dt. Okay, so this is what you actually have here, correct? So if you see carefully, sir yesterday lecture how to identify f is equal to OGH अप्लाई करना है या बायोन्स फोर्स, मतलब जो टू क्वेश्चंस में अपने एफ बी एंड वेट का मोमेंट लिया, हेड्रोस्टैटिक फोर्स ने लिया वाई, बिकॉज okay fine, I'll come back to that. Okay, we'll see that questions also now. So see here, this is what you have, dou rho by dou x into dx by dt. But of course if you see, density is only function of x. Okay, it's given density is only function of x actually, so there is no involvement of this time here. So this time is not there, so definitely this term is 0 because this dou rho by dou t is actually 0 here. Okay, because there is no dependence of time here. Now if you see, this is equal to dou rho by dou x into, please tell me what is the rate of change of x coordinate? Tell me, rate of change of displacement. X is basically the displacement in the x direction. So what is rate of change of this dx by dt? Please tell me, what is the rate of change of this x? Dx by dt is called, look, x is this direction, so rate of change of this displacement in x direction dx by dt is nothing but velocity u, correct? So this is velocity u. So that's how we have d rho by dt is equal to d rho by dt is equal to velocity times dou rho by dou x. So what is the velocity expression given? It's given u is equal to u naught times e to the power minus 2x by L. So this is equal to u naught times e to the power minus 2x by L into the partial differentiation of rho with respect to x. So derivative of this with respect to x is how much? Rho naught into derivative of exponential is exponential into inner differentiation is minus 1 by L actually. Okay, so that's how we have this expression d rho by dt is equal to, so if you simplify this, this minus rho naught u naught by L is here, so minus rho naught u naught by L into e power minus 2x by L, e power minus x by L, so total e to the power minus 3x by L here. Okay, so this is the total function for d rho by dt. Did you all understand how we have calculated this? Because they have given you density is function of x here, so there is no time dependence. So when this is function of x, if you write d rho by dt, this is equal to dou rho by dou x into dx by dt. This dx by dt is nothing but the velocity u. So u into dou rho by dou x, u expression is given, dou rho by dou x we have calculated, this is the expression. Now at what location they are asking you? The rate of change of density at x is equal to L. So what is the meaning of this? This value has to be calculated at x is equal to L, which means you need to replace x is equal to L here. Okay, so if you replace, we'll get do by dt at x is equal to L is equal to, so if you simplify, if you keep x is equal to L here, so minus rho naught u naught by L into e to the power minus 3 times of L by L. So this gets cancelled. So this is minus rho naught u naught by L into e to the power minus 3. So this is the rate of change of density at this location. Clear? So minus rho naught u naught by L into e to the power minus 3. So at the location x is equal to L, the rate of change of density is given by this value, which is minus rho naught u naught by L times e to the power minus 3. Clear? Yes? So please type in the chat box. Is this clear to all of you? So of course the answer for this is minus rho naught u naught by L into e to the power minus 3. So B is the correct answer in this question. Clear? Did you all understand? Basically, whenever certain function is given, you need to go for the chain rule of differentiation and then you need to get the coordinates. And of course, I know how you have calculated the acceleration components ax, ay and az. Okay. So questions में equation use करने में problem होता है. Yeah, definitely I know you are facing little problem in using the equations, but actually if you see this chain rule is means whenever some physical quantity is changing with respect to certain variables, space, time, whatever the case, you actually need to go for this chain rule of differentiation if they ask you for the change. Okay. How dx by dt is coming you? Please explain. Yes, because you know velocity is nothing but rate of change of displacement, correct? So the displacement in this direction is, if you measure from horizon, if you measure this displacement of x, then the velocity in this direction, which is u of course, is given by rate of change of this displacement. Okay, so u is equal to dx by dt. Clear? That's how I have replaced this dx by dt here in this expression as u. Okay, Pratik? Clear? So please type in the chat box. Is this question clear to all of you? Just you apply the chain rule of differentiation and you replace this dx by dt value as velocity in the x direction. That's it. Clear? And once you have the function, substitute, calculate the derivatives, substitute the point x is equal to L. Clear? क्लियर? मेहता राज सर buoyancy force and weight का ही मोमेंट लिया, हाइड्रोस्टैटिक फोर्स का कंसीडर क्यों नहीं किया? प्लीज एक्सप्लेन कर दीजिए. लुक, व्हाई आई हैवंट टेकन हाइड्रोस्टैटिक फोर्सेस? लुक, actually buoyancy is nothing but the hydrostatic force acting on the solids. Okay, look, on curved surfaces you calculate the hydrostatic forces, but whenever some solids are replaced inside the system, inside the fluid, you actually calculate the buoyancy force. So the hydrostatic force acting on the solid is nothing but the buoyancy force. Okay, so I actually have considered the hydrostatic forces. Clear, Mehta? चेंज होने वाले क्वेश्चन में चेन रूल लगा सकता है. या बेसिकली व्हेनेवर दे आर आस्किंग यू फॉर द चेंज ऑफ एनी क्वांटिटी, यू गो फॉर द डिफरेंशिएशन. ओके, डेरिवेटिव इज नथिंग बट चेंज. I think you all need a good division in maths classes, na? How many of you are waiting for maths classes? Please type in the chat box. How many of you are waiting for this differentiation, integration, all these things in maths? You know, okay, very soon we'll definitely come up with this maths courses. Okay, don't worry. When we take mathematics classes, we'll definitely explain you each point by point. Clear? No issues. But this is just a fundamental. That's why, even though without writing this directly, I have given you some background of this chain rule of differentiation. Clear? Okay, fine, definitely. So good, let's go for the next question quickly. So this is the case. Given the velocity field v bar is equal to 10x square by I bar, 15x by j bar, 25t minus 3x by k bar. So look, we all know how to calculate the acceleration, correct? Look, how to calculate the acceleration. See here, let velocity profile is something like u times of I plus v times of j plus w times of k. Now when you know acceleration is nothing but differentiation of this vector. So if you differentiate this, a bar is equal to dv by dt, then what you will get as the components, du by dt I bar plus dv by dt j bar plus dw by dt k bar. Only one question I have kept on acceleration, so this is k bar. Now you want to calculate the derivative of this u, correct? But normally you know, in this velocity vector, u can be function of x, y, z and time. V can also be function of x, y, z and time. W can also be function of x, y, z and time. So now, please tell me, if I want to calculate the changes in this u, if I want to calculate this change in u du by dt, do I need to again apply chain rule and calculate the values? Yes or no? So please tell me. You know, u is actually depending on 4 variables, x, y, z and t. Then in that case, whenever u is depending on x, y, z and t, if I want to calculate the differentiation of this, should I again apply chain rule? So please tell me. Praful, Dhaval, Rahul, Mehta, Amit, Vishal, all of you guys. Yes, Abhimanyu? Correct? We need to go for the chain rule. Okay. So whenever you go for the chain rule, see what happens. Du is equal to dou u by dou x into dx plus dou u by dou y into dy plus dou u by dou z into dz plus dou u by dou t into dt. Correct? These are the expressions. So if you divide with dt all over, you have dt, dt, dt and dt here. Okay. So if you simplify, this value is 1 anyhow, this is 1. So if you write the total expression for the acceleration component in x direction, dou u by dou t plus, now please tell me, all of you, everyone should tell me, dx by dt. What can I replace this dx by dt? Similarly, this dy by dt, rate of change of displacement in y direction, rate of change of displacement in z direction. So please tell me, what are the values we can substitute there? V, u, v and w, correct? So this expression is basically u, this expression is nothing but v, and this expression is nothing but w, correct? U, v, w. So if you replace u into dou u by dou x plus v into dou v by dou u by dou y plus w times of dou u by dou z, correct? This is the x component of acceleration in any flow in general. Similarly, if you take y coordinate, ay is equal to dou v by dou t plus u times of dou v by dou x plus v times of dou v by dou y plus w times of dou v by dou z, correct? Similarly, az is equal to dou w by dou t plus u times of dou w by dou x plus v times of dou w by dou y plus w times of dou w by dou z. These are the components of acceleration in x, y and z direction. So at which point? Point is not given. Okay, point they have missed, I think. Given the velocity vector, the magnitude of total acceleration of a fluid particle is dash units. Okay, they have missed the point. I think the DTP has missed it somehow. Sorry. Okay, so we'll calculate at some point. Okay, so forget about this answer, but I'll show you how to calculate the acceleration functions and then we'll substitute some point. Okay, I think they have missed the point in the typing, but okay, the magnitude of the total acceleration of a fluid particle at some location has to be given. Yes, they missed the point. Okay, sorry, we'll make sure that point is there. We'll take some random point and we'll calculate the acceleration. Okay, main idea is to make you know how to calculate the acceleration. Okay, clear? So we'll do that. Okay, so first of all, let us calculate these values. So these are the components of acceleration in x, y and z directions. Okay, now if these are the acceleration components, let us see what are the given functions. U, x component of velocity. So what is x component of velocity? 10x square y. So 10x square y. Y component of velocity v, which is given by 15 times of xy, 15 times of xy, and w component is given, which is 25t minus 3xy. So 25t minus 3 times of xy. Okay, so 25t minus 3 times of xy. So let us substitute these values. So first of all, tell me one thing. Dou u by dou t, is there any time in this function? Please tell me, is there any time in this function? If you have u is equal to 10x square, then do you have any involvement of time in this function? Please tell me. Means u is changing only with respect to x comma y. It is not changing with respect to time t. So please type in the chat box, is there any dependence of time on this u? No, correct? So that's why if there is no time, means if you differentiate this function partially with respect to time, you know this value is 0. Dou u by dou t is 0, correct? Because if you see, there is no involvement of time here. Similarly, dou u by dou z, if you see there is no involvement of z at this location, so definitely this dou u by dou z is also 0. Okay, next coming to here, in v also there is no time, then in v also there is no z. W, you cannot write dou w by dou t 0 because you have 25t here. There is dependence of t on w, so this term is not equal to 0. But there is no involvement of z here, so we'll write dou w by dou z is equal to 0 here. Okay, so now if you see, if you write the expressions, this implies acceleration in x direction is equal to u. What is u? 10x square y into dou u by dou x. So what is dou u by dou x? If you differentiate this function with respect to x partially, you will get 20 times of x y. plus v into dou u by dou y. If you differentiate this with respect to y partially, you have 10x square. Okay, you have 10x square. So this is the total acceleration in the x direction. Similarly, ay is equal to dou u is 10x square y into dou v by dou x. If you differentiate this with respect to x partially, you have 15 times of y plus v, which is 15 times of xy into dou v by dou y. So dou v by dou y is 15 times of x. Similarly, az is equal to dou w by dou t. So if you differentiate this complete function with respect to t partially, this differentiation is 0. Partial derivative of 25t is 25 plus u is 10x square y into dou w by dou x. If you differentiate this partially with respect to x, you will have minus 3y, because with respect to time it is 0, with respect to this x we have minus 3y plus v into dou w by dou y, which is minus 3x, and of course dou w by dou z is 0. This is how we get the acceleration components at this section. Okay, so once they give you some point and time value, you can substitute here definitely. Okay, so I think point is missed. Okay, so let us take one simple point at 1 comma 1 comma 1. Let us suppose, for example, let us assume 1 comma 1 comma 1. This answer won't match now because point is not there, so we'll take some random point. Let us assume 1 comma 1 comma 1, for example. Okay, simple case I am taking. So if you take 1 comma 1 comma 1, then you need to substitute x value as 1 in all these 3 equations, y value as 1 in all these 3 equations, z value as 1 in all these 3 equations. Let us suppose if they give you 1 2 3 some different point, you will take x is 1 in all these equations, y equal to 2 in all these equations, and z is equal to 3 in all these equations. Clear? Am I clear to all of you? So please type in the chat box. Is this understandable to all of you here? Is this understandable to all of you? Clear? So please type in the chat box. I hope you are understanding. Depending on the points what they give you, x, y, z values, you substitute the corresponding x, y, z, and of course in some equations if time also comes out, you can substitute the t value also. Okay, so this is how you will get the answer for this. Okay, so now at 1 comma 1 comma 1, for example, if you take at 1 comma 1 comma 1, this implies ax is equal to how many units? If you put 1, 10 into 20, 200 plus 150. So 200 plus 150. So total 350 units. Meters per second square or centimeters per second depending upon the coordinates. Ay is how much? 10 into 15. 150 plus 225. 150 plus 225. Total 375. Okay, so 375 units. Next, Az is how much? If you put x equal to 1, y equal to 1, z equal to 1, 25. This is minus 30 and this is minus 45. So total minus 45 minus 30 minus 75. Correct? So minus 45 at x equal to 1, 1531.9. 1531.9 you got at x equal to 1, y equal to 2 and z is equal to 3. Correct? Abhimanyu, do you mean x equal to 1, y equal to 1 and z equal to, x equal to 1, y equal to 2 and z is equal to 3. Correct? Is that the coordinates you mean? Okay, so fine. Anyhow, if you substitute 1, 2, 3, you could get some different answer. Okay, so if you see at z is equal to 1, this is minus 30, minus 45, minus 75, plus 25. So minus 50 units. So this is the acceleration components. Means if these are the acceleration components, the acceleration vector is how much? 350 times of I plus 375 times of J minus 50 times of K bar. Okay, so this is the acceleration vector. So if you want to calculate magnitude of this vector, root of, you know how to calculate magnitudes of vectors. Basically, if some vector is given to you, you can calculate it using 350 square plus 375 square plus minus 50 whole square. So this value, if you simplify, you will get some value in units actually. Okay, so you can calculate this value. Okay, so there is no z. Okay, z is not there, only x and y are there. Okay, so x is equal to 1, y is equal to 2. Okay, good. So if you put x equal to 1 and y equal to 2, you are getting this value which is given in the question. Okay, so you can substitute and you can get the values also. Clear? So this is, if you see 200 x square y, this is 150 x cube y. Okay, you will need to substitute basically. Okay, so is this clear to all of you? So please type in the chat box. Did you all understand how to calculate the accelerations? So please type in the chat box. Is this clear to all of you? Did you all understand how to calculate the accelerations whenever certain velocity vector is given? Because the questions on calculation of accelerations is very much, most repetitive kind of questions in GATE examination. So I thought of keeping one simple question on accelerations. Okay. and its main crux is identifying how you get these equations, and these equations are very important because you keep on using them in incompressible flows, or means basically internal and external flows. Okay, we use these equations a lot of times, so that's why I've given you some clear idea on how these equations turns out. Clear? X equal to 1, y equal to 2, acceleration is okay 515.3. let us calculate 350 square. Let us take a virtual calculator. So get calculator. So 350 square, 350 square plus 375 square, 375 square plus 50 square. Okay, so if you simplify this, square root of this 515.38, 515.38 units. Okay, so this is how we have 515.38 at this particular location at x equal to 1, y equal to 1, and of course only two variables are there in the acceleration, so 1 comma 1, x equal to 1 and y is equal to 1. Okay, but if you take x equal to 1 and y equal to 2, you are getting some different answer. Obviously the points changes. Okay, but the main idea is you should know how to calculate the acceleration. So is this clear to all of you? Clear? Okay, yes or no? So type in the chat box. Shall we go for the next question? All of you, Dawal, Amit, Tripathi, Harun, Rohit, Abhimanyu, all of you guys. So please type in the chat box. Shall we go for the next question? Clear? Is this clear to all of you? Shall we go for the next question? Okay, yes, great. Yes, next. So this is the next question. So see here, for a steady two-dimensional incompressible flow through a nozzle, the velocity field is given by V bar is equal to U naught times of 1 plus 2x by L times of I bar, where x is the distance along the axis of the nozzle from the inlet plane and L is the length of the nozzle. The time required for a fluid particle to travel from inlet to exit of the nozzle actually. Okay, so what they are telling you is, you have a nozzle like this, you have a nozzle like this. So this is some nozzle. So obviously this nozzle has some axis. So this nozzle has some axis like this. Okay, so whenever this nozzle has some axis, then this is the inlet section, this is the inlet, so this is the inlet and this is the outlet. Okay, here is the outlet. So if you see, this is your inlet and this is your outlet. Okay, so inlet and outlet. So whenever you have this inlet and outlet, now try to understand this thing. There is one particle, there is one fluid particle which is moving in this direction, obviously along the axis. Now the velocity of this particle in this x direction, so let us suppose if this is the x direction, so let us take this point as origin for example, and let us suppose this is the x direction for example. Okay, so if this is the x direction, now what it's happening, the velocity of the particle in that region, in that location is given by V bar is equal to U naught times of 1 plus 2x by L times of I bar, which is nothing but this I component is nothing but U. So velocity in this x direction is given by U naught times of 1 plus 2x by L. Okay, so you have this velocity profile. Okay, so once you have this, U is equal to U naught times of 1 plus 2x by L. Now the particle is starting at this location at the inlet. So let us suppose time t is equal to 0. The particle reached here. Time t is equal to t. Okay, within time t, the particle reached to that location. Time t is equal to 0 to time t is equal to t. So they are asking you what is the time if this is the velocity at any given location. Obviously, you know, the particle will accelerate in a nozzle. Okay, because physics that tells you is in a nozzle flow actually accelerates. So whenever flow is accelerating, definitely that means as x is increasing, velocity should increase. Correct? So that's how it's given. As x is increasing, this u value will increase. Okay, of course it's a nozzle. Did you understand how this equation is justifying the flow through a nozzle? So please type in the chat box. First of all, did you understand how this equation is justifying the flow through a nozzle? Because as your x distance increases, means from the inlet as you go inside, the velocity of the flow actually increases. Clear? Yes? So is this clear to all of you? Now we'll see what mathematics we need to do, but right now, did you all understand this? And length of the nozzle is given. The length of the nozzle is basically L. Okay, so length of the nozzle is L. Okay, now if length of the nozzle is L, then let us see. If you see, U can be written as dx by dt. Dx by dt is equal to U naught times of 1 plus 2x by L. Now if you see, if you slightly convert this, 1 by 1 plus 2x by L times dx is equal to U naught times of dt. Okay, U naught is some constant value. Now this is the equation at any point within the motion. Okay, yes, converging increase velocity. Okay, so now if you see this case, if you integrate this between two limits, Initially when x is equal to 0 means when the particle is here, the time t is equal to 0. Now you are interested in finding the time that this particle need to cross the nozzle, means to bypass the nozzle. So if you see, let us suppose at some time t is equal to t, can you tell me what is the x coordinate? If you are interested in calculating this total time, and let us suppose if I take the total time as t, at time t equal to 0, the location of the particle x is equal to 0. Now at time t equal to t, let us suppose if the particle reached here, can you tell me what is the limit here? L, capital L, correct? So capital X is equal to capital L. So let us do the integration, then you will get the value of time t. Okay, it's a simple question again, but understanding the things is easy. So first 2-3 questions I've kept some common questions which can be understood easily, and you will go. Okay, so now if you do this integration is how much? 1 by 1 plus 2x by L. So integration of 1 by, I'll give you this expression, integration of 1 by a plus bx dx. So you know that this value is 1 by b times of ln a plus bx, correct? Plus constant, of course, you have some arbitrary constant also. So integration of 1 by a plus bx is actually this value, which you know from your basic integration knowledge. Okay, because if you differentiate this, you will again get the same result, 1 by 1 a plus bx. So if you simplify, if you apply this, integration of this is ln 1 plus 2x by L with a division of 2 by L, correct? If you do division with 2 by L, you will get L by 2 here. Yes or no? Correct? Because if you see to this ln, if you divide with this 2 by L, you will get L by 2 multiplication. So this value within the limits, what are the limits here? X is equal to 0 to x is equal to L. So these are the limits, and u naught is a constant. If you take out of integration of dt is nothing but a t. When you substitute the limits, t minus 0 directly. Okay, so this is what you have. Now if you substitute here, this gives you L by 2 times of when you substitute x is equal to L gets cancelled, and you have ln 1 plus 2 ln 3. Okay, so when you substitute L, that value is ln 3 minus, when you substitute 0 here, log 1 plus 0. So 1 plus 0 is 1, and log 1 is 0 actually. Okay, so this limit is 0. So this is equal to u naught times t is what you have. So what is the expression for time t for the particle to cross the nozzle? L by 2, L ln 3 by 2 divided by u naught. So L by 2 times of u naught into ln 3. Okay, log 3 to the base e. So this is the time t for this value. Clear? So this is how you get the total time that the particle requires to cross the nozzle. Clear? Got it? So this is how we have done this, but simple thing, but of course you need to do some integration here. That's it. Okay, so one integration and substituting will actually give you the value. So 2 times of L by 2 u naught into ln 3. So L by 2 u naught into ln 3, which is in option B, of course. Okay, so B is the correct answer. Okay, so clear? Did you all understand how we can do this? Yes, simple question, just from the basics, but you need to apply them really carefully. Are you all liking the questions? So please type in the chat box yes or no. Are you all liking the questions? Yes. Next question. So let us go for the next question. So first 2-3 questions I gave you to just understand the basic things. Okay, so from now we'll go on to some some likely next level things. Okay, so this is one question. So see here, assume the temperature of the exhaust in an exhaust pipe can be approximated by temperature at any location is given by T is equal to T naught times of 1 plus A into e power minus bx into 1 plus c cos omega t, where T naught is 100 degrees Celsius, A is 3, B is 0.03 meter inverse, C is something, omega is also given some constant. If the exhaust speed is a constant 2 meters per second velocity, means if the exhaust is moving out of the exhaust pipe at a constant velocity of 2 meters per second, then the time rate of change of temperature of the fluid particles at x is equal to 4 meters and t is equal to 0. What they are asking you? Time rate of temperature, time rate of change of temperature temperatures, correct? So they are asking you dt by dt. Okay, means derivative of temperature with respect to time, correct? Rate of change of temperature with respect to time is what they are asking you. So now you know this temperature is a function of x, it is also a function of t actually. Okay, so this implies dou t by dou x into dx by dt plus dou t by dou t into dt by dt. So this is the total chain rule if you apply. So this dt by dt value is 1 actually here. Okay, so if this value is 1, now let us calculate the expression. So t is given by some expression t naught into 1 plus a into e power minus bx, 1 plus a into e to the power minus bx multiplied with 1 plus c cos omega t, 1 plus c times cos omega t. Okay, so this is what you have here. So 1 plus c cos omega t. So let us calculate these values. Now again, this dx by dt is nothing but velocity in the x direction, u. Okay, so let us say here dou t by dou x. So what is dou t by dou x here? If you calculate dou t by dou x, if you differentiate this complete expression with respect to x partially, this t naught is a constant, this total function is also constant. So t naught times 1 plus c cos omega t into, if you differentiate this partially with respect to x, you know, derivative of 1 is 0, a is a constant, into in differentiation of e power minus bx is minus b times e to the power minus bx. So this is what you have here. Okay, so this is the total value. Next, what is dou t by dou t? Dou t by dou small t is equal to, if you differentiate again, t naught into this 1 plus a into e to the power minus bx, this is constant value, multiplied with, if you differentiate this with respect to time, differentiation of 1 is 0, c is constant, derivative of cos minus sin omega t into omega. Correct? So this is the value. So total, this is the function. Okay, so now u value is also given. What is u? It's given the exhaust speed is a constant 2 meters per second. So the meaning of this function is this u value is actually 2 meters per second. Okay, so u value is 2 meters per second. Okay, so let us see here. So if you see dou t by dou x into u into this value plus dou t by dou t, this value is 1 actually. Okay, so now if you see here, let us substitute dt by dt is equal to, so let us substitute these values, u 2 times of dou t by dou x. So dou t by dou x is this value 2 times of t naught into 1 plus c cos omega t times minus ab times e to the power minus bx, this value plus dou t by dou small t, which is t naught times 1 plus a into e to the power minus bx into this value minus c omega sin omega t. This is the value. Now at what location they are asking you the coordinates? They are asking you the change of this temperature at x is equal to 4 meters and time t is equal to 0. Correct? So let us keep x is equal to 4 and t equal to 0. At x is equal to 4 meters and t is equal to 0 seconds. Okay, t is equal to 0. Now tell me, whenever t equal to 0, what is the value of this sin omega t? Whatever may be the value of omega, it's finite value of course. So whatever may be the value of omega, when you put time t equal to 0, tell me what is the value of this sin omega t? What is the value of this sin omega t? 0. Correct? Because at time t equal to 0, this sin omega t is actually 0. Okay, so this value is 0. Okay, now if this value is 0, this complete term is 0. Correct? So if you see at this location, if this one quantity is 0, then this complete term here is 0. Now let us go for this dt by dt, and of course this cos omega t value is 1, because when you put time t equal to 0, cos 0 comes out, so the value is 1. So 1 plus 1 2, 2 into 2 2, so total 4 t naught. This implies dt by dt at x is equal to 4 meters, t is equal to 0. This value is equal to 2 plus 2 total. Okay, you have c here. So 2 times of 1 plus c, 2 times of 1 plus c times t naught into, when you put x is equal to 4 minus ab times e to the power minus 4b. This is the value. Now let us read the values of the constants t naught, a, b and c. Okay, so from this let us see a value is how much? A is t naught is 100 degrees Celsius first of all. So t naught is 100 degrees Celsius. Okay, what about a? Small a. Small a is also given. Small a is 3. A is 3. B is, what is the value of b? 0.03. So 3 into 10 to the power minus 2, let us say 0.03 meter inverse. So this is meter inverse, this is meter inverse, and a is of course dimensionless constant. Okay, so because it has to be multiplied to some exponential function. And what about omega? 100 radians per second. So omega is equal to 100 radians per second. And anyhow, I think we don't need any omega there, so let us substitute this values. So 2 times of 1 plus c. Okay, c value is also there. What is c? C value should be there. C is equal to 0.05. Okay, C is equal to 0.05 is what you have. Okay, so let us substitute 1 plus C 1.05 times units. Look here, let us check the units, because if you see what are the units of T naught, the options are given in degrees Celsius per second, so you can directly take this value in degrees. For example, if they give you in Kelvin per second, definitely should convert this T naught to Kelvin. Okay, so here it's given in degrees Celsius, so let us substitute directly into minus A into B. So what is A into B? A value is how much? A is 3 into B. So 9 into 10 power minus 2. 9 into 10 power minus 2 into e to the power minus 4 times of B. So 4 times of B is how much? 4 times of B is 12 into 10 power minus 2. So minus 0.12. So this is the total value in degrees Celsius per second. We'll do one thing. We'll cancel this 2 zeros and this 10 power minus 2 here. Okay, so if you cancel out, let us calculate what is the value. Okay, so if you calculate this value, you will get e to the power minus 0.12. So minus 0.12 exponential of this, exponential of e power minus 12 is 0.086 multiplied with 18 into 1.05 multiplied with 18 into 1.05. Okay, so if you see, this is the value but with a minus sign, because if you see there is a minus here, there is this minus, so minus 16.76 minus 16.76 degrees Celsius per second. Okay, clear? Minus 16.76 degrees Celsius per second is the rate of change of temperature for this velocity, for this temperature profile, which is changing with x and time. Clear? Got this answer? Minus 16.76. Where is it? Okay, minus 16.8. If you round off to one decimal, minus 16.8 degrees Celsius per second is the correct answer. Clear? So did you all understand now what are the functions they give you, how to calculate the rate of changes of any quantities? Because such kind of questions came in GATE in earlier years. So that's why I thought of keeping some questions like this. Clear? But it's very much important and very much important for you to understand how these things actually work out. Okay. Next, so this is the next question. So see here, an incompressible flow around a circular cylinder of radius A is given by the stream function. So stream function is given, psi is equal to minus u times of r into sine theta plus u a square sine theta by r. This is in polar coordinates. Okay, so this is in polar coordinates. Polar coordinates. Polar coordinates, of course in 2 dimensions. Okay, where u represents the stream velocity, free stream velocity. Which of the following statement or statements is or are correct regarding the radial and azimuthal components of velocities at r is equal to a? So basically this is an MSQ, so multi-select question. So they are asking you. Okay, now let us see here. So basically this is this question. So stream function is given. So basically they are telling you there is a cylinder and there is a flow across the cylinder. Okay, so means basically flow around a cylinder. If you have a cylinder, there is some flow around a cylinder. Okay, of course when I'm talking about potential flow questions, we'll deal this case in very much importance, that whenever there is a cylinder, then if there is some flow above the cylinder, means around the cylinder, we will see different things like stagnation points, pressure regions, low pressure values, all these things. But right now for us, this is just a stream function. We don't know, there is some flow. For that flow we have a stream function. Okay, so now what is the relation between radial components of velocities and azimuthal values here? So now let me ask you one question before solving this question. Okay, let me ask you this question. I need 2 slides. Okay, so now if you see, let me ask you this question. Have you heard this word Cauchy-Riemann equations anywhere? Cauchy-Riemann equations, and sometimes you call them CR equations. Sometimes you call them CR equations. So please type in the chat box. Have you ever seen this? Have you ever heard of this Cauchy-Riemann equations or CR equations? In complex calculus and all, you will get them normally. So please tell me. Have you ever seen this? No. Okay. Fine. If you haven't seen, look, I'll give you some idea. Okay, so some basic idea in maths, so then we'll go for this question. Okay, clear? Okay, so we'll definitely see some idea on mathematics and then we'll start this question. Okay, so now let us see. Normally if you have this velocity profile, v is equal to ui plus vj, okay, and let us suppose if the flow is irrotational normally, okay, so then there exists a velocity potential function phi, okay. So for every irrotational flow, for every irrotational flow phi exists, okay. So phi is actually called the velocity potential function. So phi is called velocity potential function, okay. So this phi is called the velocity potential function, okay. So this velocity potential function is in such a way that the partial derivatives of this velocity potential function gives you the actual components of velocity, okay. And please keep in mind phi exists only for irrotational functions, okay. How you decide whether a flow is irrotational or not? Once you know the velocity vector, if you calculate curl of that velocity vector, because you all know angular velocity vector is nothing but, angular velocity vector is nothing but half times of curl v bar, correct? You need to do del cross v, del cross this v bar, correct? I normally in all my fluid mechanics classes I derive this equation, but right now since this is a quick go, I'm just giving you the equations, okay. So omega bar is actually equal to half times of curl of this velocity vector, curl v bar. Now if you see, if this flow is irrotational, means if the rotation of the flow has to be 0, then definitely this curl v has to be 0, and that's why in maths and all you'll they'll teach you one thing. If curl of any vector point function is 0, they call that vector point function as irrotational vector point function, okay. So in mathematics there is a rule, whenever any vector point function, if you see this has 3 components u, v, w, and all these depend upon x, y, z. So whenever this curl v is 0, definitely there exists a scalar point function such that this f bar is equal to gradient of phi, okay. So look, there is, okay, let me explain you in a detailed way. Let us spend some time, no issue. So see here, at least before this you will get clarity on this. So for every irrotational flow, phi actually exists, okay. So I'll give you one equation. Let us suppose you have some function, okay, f bar of x, y, z is equal to some fxi plus fyj, means y component, j component, and z component, okay. So x, y, z components. Let this x component be something like x square, 3x square, yz for example, next into I bar plus x cube z j plus x cube y k bar, okay. So let us suppose there is some vector point function like this, for example, okay. There is some vector like this. I am just giving you some mathematical help so that you can work out the things, okay. So this is u component, v component, and w components of this function. Now if you see, if you calculate curl of f bar, then what you will get? I, j, k, dou by dou x, dou by dou y, dou by dou z, and u, v, w, correct? Means this components fx, fy, and fz. So 3x square y z, x cube z, x cube y actually. So this is one curl, okay. So if you calculate this value, you will see what you will get. I bar times of dou by dou y of this function, which is x cube. So if you differentiate this function partially with respect to y, you will get x cube, minus dou by dou z of this quantity, again gives you x cube, minus j bar times of dou by dou x of this quantity, gives you 3x square y, minus dou by dou z of this quantity, again gives you 3x square y, plus k bar times of dou by dou x of this quantity, gives you 3x square z, minus dou by dou y of this quantity, again gives you 3x square z. So if you simplify this, you see this is a 0, this is 0, and this is also 0. So first thing you know is this curl f bar is equal to 0 bar. Now you have one particular rule in mathematics that whenever this curl f bar is 0, means if there is any vector point function with curl 0, then definitely there is a scalar function such that this f bar is actually given by grad phi, gradient of phi, okay. There exists phi such that f bar is equal to gradient of phi. For example, if you take phi value as, let phi is equal to x cube yz, if you take this scalar point function, then definitely gradient of this phi actually gives you this f bar actually here, okay. So means if you see, how will you calculate gradient? Gradient is nothing but dou phi by dou x I plus dou phi by dou y j plus dou phi by dou z k. Okay, so this is what you have actually for the calculation of f bar. So for this function, if you calculate this dou phi by dou x value, what you have here, dou phi by dou x is nothing but 3x square yz times I plus dou phi by dou y x cube z j. Similarly here x cube y k, and if you see this gradient of phi and this f bar, both are same actually. Okay, so this is one very important rule in mathematics, that whenever curl of any vector point function is 0, definitely there exists a scalar function such that this gradient of this scalar function is actually equal to that f bar. Now why we have talked about this? Because if you have any velocity vector, such that the curl of the velocity vector is 0, then definitely there exists a scalar function such that the gradient of this means dou phi by dou x is equal to u, dou phi by dou y is equal to v, and dou phi by dou z is equal to w actually. Okay, so you have this u, v and w values. Clear? Did you all understand how we come to the concept of velocity potential actually? So please type in the chat box. Is this clear to you? Okay, so you have u is equal to dou phi by dou x and v is equal to dou phi by dou y. Of course, in two-dimensional flow, if there is no w, this component won't be there. You will deal in two coordinates. U is equal to dou phi by dou x and v is equal to dou phi by dou y. So is this concept clear to all of you? Did you all understand how we write these equations? Because based on this mathematical understanding. Okay, some 4 or 5 minutes I have spent on this. Okay. Last point. So basically when curl of v is 0, you see when curl of f is 0, we came to know that there exists this function phi such that this gradient and f are equal. Similarly when curl of v is 0, there exists this function such that gradient of phi means dou phi by dou xi plus dou phi by dou yj plus dou phi by dou zk is equal to ui plus vj plus wk. So if you equate the components, you will get u is equal to dou phi by dou x, v equal to dou phi by dou y, w is equal to dou phi by dou z. Clear? Okay, so is this clear to all of you? Okay, Amit. Now, if you have this, now let us see what are the Cauchy-Riemann equations. Okay, so let us see what are the Cauchy-Riemann equations and how you actually calculate them. Okay, so I'm using this because this is just for your understanding I have given you. Okay. So let us see here. Now, normally, you know, for every irrotational flow, we have this potential function phi exists. Of course, phi exists, and u is equal to dou phi by dou x, and v is equal to dou phi by dou y. When this phi is in Cartesian coordinates, but actually, if you see in the polar coordinates, if you convert this into polar coordinates, means let us suppose if this v bar is something like radial velocity into unit vector in radial direction, azimuthal direction velocity into this plus uz into ez cap. So er cap, e theta cap, ez cap are the unit vectors in radial, azimuthal means theta direction and also in z direction. Okay, so whenever you have this, then here of course we are not talking about the third dimension, this is 0. So if you see again, if this vector point function is irrotational, of course phi exists in polar coordinates, and these values are given by ur is equal to dou phi by dou r, and u theta is equal to 1 by r times of dou phi by dou theta is what the expressions you have. Okay, if this is given in polar coordinates. Okay, if this is given in polar coordinates, these are the components of velocities for the potential flows. Okay, but now if you talk about the stream function, you know, stream function and potential functions are always orthogonal, and they actually form a complex potential which we talk in potential flows. But right now if you see, if you have a potential function phi of x comma y, and if you have a stream function psi of x comma y, then definitely we have dou phi by dou x, which is u of course, is equal to dou psi by dou y, and similarly v is equal to dou phi by dou y, which is equal to minus dou psi by dou x, and these equations are called Cauchy-Riemann equations. Okay, so these equations are called CR equations, basically CR equations in Cartesian form, of course. Okay, so CR equations. So if you come to polar form, these equations are like dou phi by dou r is equal to 1 by r times of dou psi by dou theta, and dou phi by dou theta is equal to minus r times of dou psi by dou r. So these are the polar form of this Cartesian equations. Okay, so in polar coordinates, the CR equations, Cauchy-Riemann equations are written in this form actually. Means if you see this dou phi by dou r is nothing but radial velocity, so radial velocity is nothing but 1 by r times dou psi by dou theta. This is one value. Then dou phi by dou theta is nothing but r times of u theta. So r times of u theta is equal to minus r times of dou psi by dou r. So if you cancel this r's, you have these two relations, that when a stream function is given in polar coordinates, radial velocity is calculated by 1 by r times of dou psi by dou theta, and azimuthal velocity is calculated by minus dou psi by dou r. So these are the two expressions for calculating radial and azimuthal velocities when stream function is given, and these are the functions to calculate ur and u theta when phi is given. So is this clear to all of you? Polar form means in place of x comma y, we replace with r cos theta and y with r sin theta. Okay, so normally to analyze any motion, you have Cartesian coordinates, polar coordinates, normal and tangential coordinates also. So polar coordinates is basically one thing with respect to which with respect to radius and theta we define the location of a particle. Okay, everything way with respect to r and theta, yes, of course. Okay, so now let us see. So first of all, did you all understand how to calculate the radial velocity direction and theta velocity direction with this ur and u theta when potential function is given and also when stream function is given? Yes, so please type in the chat box. Did you all understand how to calculate the velocities in radial and theta directions when this phi and psi both are given to you? Okay, so is this clear to you? So please type in the chat box. Is this clear to you? Did you all understand how to calculate these values when phi and psi are given to you? Okay, so if that's clear, let's go for this question. Okay, so if this much background is in your mind, because if I directly write these equations, you don't understand what's happening. So that's right. Now let us go. Psi stream function is given. So what is this stream function? Psi is equal to minus u times of r into sin theta plus minus u times of r sin theta plus u a square sin theta by r plus u a square sin theta by radius. This is what you have. Okay, so this is basically the stream function. Okay, okay, yeah, I'll repeat after the completion of this question. I'll go again. Okay, so see here. So if you calculate this ur, if you want to calculate the radial velocity at any radius and angle, so ur is given by 1 by r times of dou psi by dou theta. Correct. So let us see what is this value. 1 by r times of, now if you differentiate this with respect to theta partially, this minus ur as it is, as it is, sin theta differentiation is cos theta, plus this u a square by r is as it is, and differentiation of this sin theta is again cos theta. So this is the total radial velocity component. Means if you simplify, actually if you simplify, this r cancels this r and we'll put a r square here. Okay, so this implies radial velocity at any given location is calculated using minus u times of cos theta plus u square into a square by r square cos theta. So this is the expression for radial velocity at any radius and at any angle. Similarly, if you calculate u theta velocity in the azimuthal direction, so u theta is minus dou psi by dou r, so minus dou psi by dou r. So if you differentiate this function with respect to radius, then partially minus u sin theta is constant, minus u sin theta into derivative of this small r is 1 with respect to partial differentiation, plus u a square sin theta is constant, u a square sin theta is constant, then differentiation of 1 by r is minus 1 by r square. Okay, so this is the total velocities. Okay, so now if you simplify this minus sign and all, this minus total all over this minus can be made plus with this minus. So total you have u sin theta plus u times of a square by r square times sin theta. So this is the expression for u theta at any radius and at any angle. So this is how we calculate the expressions for u theta and also u r radial velocity. Okay, so this is for u theta and this is for u r and u theta. Now let us see the options what they are asking you. So let us read the question. which of the following statements regarding the radial and azimuthal velocities at r is equal to a, means at this point on the surface of the cylinder, let us suppose at r is equal to a is 1 point. So at r is equal to a, what are the radial component and theta component velocities? Okay, so let us see. At r is equal to a, ur is how much? Radial velocity is how much? If you put r is equal to a, this term gets cancelled out, minus u cos theta plus u cos theta, which is 0. Okay, so ur is equal to 0. Similarly, u theta is equal to how much here? If you put r is equal to a, u sin theta plus u sin theta, so total 2 times of u sin theta. So this is how we have this points. Okay, so normally we have done all this analysis, but definitely after teaching potential flows, means if I discuss you the case with flow over a cylinder, definitely by looking at this question itself, you will come to know that ur is 0. How? Look, I'll explain you simply within one line explanation. Let us suppose if there is a flow like this. Now, if this is a cylinder, let us suppose if the radius of the cylinder is a, for example. Now, tell me, let us suppose if the fluid particle, if the fluid is coming like this, then at this location it takes a curvature, correct? So at this location, when the fluid particle is coming like this, definitely it takes a curvature like this. Means there is certain amount of fluid which will try to rotate at this radius. Now tell me, at this location, is there any fluid which is actually going like this? Tell me, is there any fluid which is going radially at this location? Of course, some fluid is taking the rotation, of course, along the cylinder. But now tell me, is there any fluid which is actually going into the cylinder? Practically, is this possible? No, there is a thick cylinder which is blocking the flow. So that's why whenever the fluid is coming, it's slowly getting diverged on this. Okay, so radially there is no flow. So that's why clearly you can understand ur becomes 0 in this case. Okay, clear? Is this understanding clear to all of you? Okay, but anyhow, we'll talk about this flow over cylinders and all in potential flows. Okay, did you all understand the mathematical background behind this question and physically what we are doing, how we are calculating radial and theta direction velocities? Clear? Sorry, someone has a doubt? So u minus u cos theta hua. Sorry, didn't get this here in this case. So if you see, minus u cos theta plus this a is equal to r. So if you replace r here, this r square gets cancelled. So plus u square into, okay, got it. I made a mistake here. I have kept 2. That's what people are doubting. Okay, there is no u square here. Okay, I was thinking one step ahead. So there is only u here. Okay, this is u. This is u. Okay, sorry, it's not u square. Okay, this is only single u because just the partial differentiation of this. So there is only one u. Okay, not the square. Okay, so this is how we get the question. So did you all understand, if complex potential function, means if velocity potential function is given and stream function are given in polar coordinates, how to calculate the radial and theta direction velocities based on these relations? Okay, so ur is dou phi by dou r, u theta is 1 by r times dou phi by dou theta. Similarly, if you go for Cauchy-Riemann equations, these are the values. Clear? So when stream function is given in polar coordinates, this is how you actually calculate the radial and theta direction velocities. Similarly here. Okay, okay, fine. If r is less than a, look, normally we don't have, physically, means practically, mathematically you can get some expressions, but practically speaking, r cannot be less than a, because from the center of the cylinder till a you have the solid cylinder actually. So within that location, if you see, we actually, if I have taught you potential flows, I might have told you why we analyze this case as flow around a cylinder is we get one streamline as a circle actually. Okay, so one streamline you will get as a circle, and you know there cannot be any flow across the streamline. So we'll see there is some fluid which is getting blocked here. Okay, so this fluid is having some blocking here. Okay, so that's why we'll talk about the velocity here actually. Okay, but practically or physically, when you do this condition as flow within the cylinder, there is no flow. Okay, we'll see about this in much detail in potential flows actually. Okay, I think crash course on fluid mechanics is about to start by Amit Dikshit sir. So definitely I'm sure that he will touch you to all these things on which we are solving the problems. Clear? Okay, now let us see here. So if you check the correct options, Vi is 0. So radial component of velocity is 0. Radial component of Yeah, radial component of velocity is 0 and azimuthal direction component is 2 times of u sin theta. So A and B are correct answers. Obviously azimuthal is not 0, so this is wrong, and radial is not 2 u sin theta. So C and D are wrong options. A comma B are correct options here. Clear? So back page कर दीजिए, this page. Okay. Now if you see this, basically I am telling you, if velocity potential is given, this is how you calculate radial and theta direction velocities. If stream function is given, this is how you calculate radial and theta direction velocities. Okay, these equations are called Cauchy-Riemann equations. Hopefully when I teach you mathematics later, maybe after some time, then definitely I'll show you how these equations comes out. Okay, we'll take some analytic functions and we will work out this. Okay, clear? So shall we go for the next question? Okay, so let's go for the next question quickly. So if you see, there is a cone. Water enters the bottom of the cone in figure. So if you see, there is a cone in figure. Okay, so there is some small opening, diameter d is there. Okay, so there is a small hole of diameter d, means if there is a cone, slightly have cut some portion so that there is some entry for the fluid. Okay, so the cone in a figure at uniform increasing average velocity v is equal to kt. So if you see, there is one velocity profile here. There is some fluid which is entering this cone, and what is the velocity of this entering fluid? Area of cross section is constant, but this fluid is entering at a velocity v is equal to k times of t, means velocity is increasing with time increasing. Okay, if d is very small, means if this diameter which is here is diameter d, which is very small. Okay, d is very small. The correct analytical formula for the water surface rise. So tell me, first of all, try to understand the physics, what's happening here. There is a cone, so there is an opening at the bottom of the cone. So what happens if you keep on sending water, then definitely this water level in the cone will keep on increasing, correct? So this increase in water level of the cone, they have mentioned h of t, height of the water surface with respect to time. For the condition h is equal to 0 at t is equal to 0. So means at time t is equal to 0, there is no water in the cone, so you started sending water. But this sending water velocity is actually depending on time, so v is equal to some constant times of time. Okay, assume incompressible flow. So assuming incompressible flow, they are asking you what is the correct expression for this increase of water level h with the time. That's what they are asking you. Did you all understand the question first? We'll see how to solve the solution, but did you all understand this question? How to, means what they are asking you in the question? When this cone is not having any water at time t equal to 0, you started sending water into the cone. So the sending velocity is actually depending on this function v is equal to kt. Then depending on the water you are sending, the water level in this cone is rising. So they are asking you what is the function of this rise h with respect to time t. Clear? This is what they are asking you. Okay, yes, clear? So let's see how to analyze this situation. But is this clear to all of you? Did you all understand what they are asking you in the question? We'll see how to solve. But clear? Yes. Okay, so now let us see here. If you take this control volume at any time t, for example, if you take this volume, for example, if you take this volume, then in this volume, if you apply continuity equation, in that control volume, you know, mass flowing in minus mass flowing out, m out, is nothing but a rate of change of mass within the control volume, correct? Yes or no? So please tell me, mass flowing in minus mass rate which is coming out of the cone is actually equal to the rate of change of mass within the control volume. Normally if you take any volume, the difference in the mass inside that volume is nothing but the difference between these two, correct? Now in this case, if you see, there is only mass that is coming in, no mass is coming out. So m dot out is actually 0. Okay, so m dot out is actually 0 here, correct? So m dot out is 0 because only there is certain fluid which is entering the cone, but nothing is actually leaving the cone. Now let us write the expressions for m dot in. So m dot in is equal to mass flow rate that is flowing in is equal to, so what is the mass flow rate that is entering at this section? Density into area of cross section at this location into velocity. Look, whenever you are writing discharge A into V, you should make sure A and V are perpendicular to each other. Okay, because the things comes from the dot product. The rise will not be accounted, it will be accounted. That's what we are calculating. What is the rise? within the time, with time. Okay, that's what they are asking you. Okay, so whenever you're writing discharge, you should make sure that the area of cross section and the flow velocity both are normal to each other, because you see discharge is given by this formula, Q is equal to V bar dot n cap dA. Okay, of course, if you see, this is the expression for discharge. Okay, so if you see, your area and velocity both are normal to each other. So now if you see, it is a vertical cone. So let us suppose if this is the cross section, the cross section is horizontal, so the velocity should be exactly vertical. And if you see, the velocity is exactly vertical, so what we will write, m dot in is equal to density times area of cross section, which is pi by 4 d square, is the area of cross section, into flow velocity, which is v, which is some function of t. So this is small mass which is flowing in. So we write dm in, or m dot in minus m dot out. Let us write it. Mass of control volume. So what is the mass of control volume? Definitely density of the fluid into volume. So what is the volume of this cone? Actually, if this d is very small, means if you assume this as a complete cone, then what happens at any instant, if the height is h and if this diameter is d, for example, okay, if this diameter is d, okay, if this diameter is d at any instant, then you know, or let us take radius r, better. So if you take radius r, if you take this radius r example, okay, then from this triangle, if you take, if this d is very small, means let us suppose if you have like this, okay, this d is very small, so if you assume it is a closed triangle, then this is height h, this is r. So if you see, if this angle is theta, you can write tan theta is equal to r by h. Okay, so this r radius can be written as h into tan theta. Okay, so this can be written as 1/3 pi r square. So what is r square? H square tan square theta into h. Correct, this is what you have. 1/3 pi r square h is the volume of the cone. So if you want 1/3 pi r square h, h is known to you, but actually you need to convert this smaller, this capital R in terms of h, which can be done by this equation. So theta is the angle of this cone here, semi-cone angle. So tan theta is equal to r by h from this triangle. So if you see, why I'm calling it triangle, because I mean, if d is very small, d by 2 is much smaller. So I am assuming that it is a triangle. It's, both ends are closed, almost closed. Okay, so now if you see, this is the expression for the mass of the control volume. This is m dot in. So if you replace in this expression, this gives you m dot in, which is rho times of pi by 4 d square into v. So this value is equal to rho times of 1/3 pi h square tan h cube tan square theta, actually h into h square into h. So this is h cube tan square theta. But of course, if you see, we forgot one thing, m dot in is equal to m dot in, which is rho times of pi by 4 d square into velocity. This is equal to this derivative d by dt of this quantity. Okay, d by dt of this quantity, because mass of control volume is this at any given time, and this is the mass flow which is going in. Okay, so now if you see, let us cancel some constants. It's an incompressible flow. Density can be taken as constant. Pi is a constant, actually. Okay, so now if you simplify the things, we have, if you simplify the things, you have 3/4. So if this 3 comes onto the top, 3/4 d square into v, and of course tan square theta is also there. So if you bring this tan square theta also, so 3/4 d square v tan square theta. So this expression into dt is equal to derivative of this h cube. Okay, so this is what you have, because tan square theta you have moved here, this 3 you have shifted here. So on right hand side we have only this. Okay, so initially if you integrate this, because this is the derivation of h cube, so if you integrate this between the limits when time t is equal to 0, because all these are constants, all these terms are constant. So 3/4 d small diameter is constant, tan square theta cone angle is constant. So from t equal to 0, h is also equal to 0. At time t is equal to t, what is the height? Let us suppose if this is h, now you need to calculate the value of this h actually here. Clear? So they know that at time t is equal to 0, this small h is 0. After some time, this height of the water in the tank is actually h. So they are asking you at time t, what is the height h? Okay, so if you do the integration, this 3/4 d square by tan square theta is constant. Okay, so this implies 3/4 d square tan square theta is constant. So integration t is equal to 0 to t is equal to t, you have velocity. Velocity is nothing but k times of t. Okay, velocity at any time t is given by kt. This is equal to integration of differentiation. Both these are inverse operators, so these things cancel. So the integration will have h cube. That's it. Okay, because if you see, this integration of differentiation is actually both are inverse operators. So if you differentiate this, you will get th square dh. Again, if you integrate this, you will get h cube. Okay, so substituting limits will give you h cube on the right side. Okay, so now if you see this value, 3 by 4 d square k tan square theta. Okay, so 3 by 4 d, oh I'm sorry, tan square is in the denominator, so tan square is in the denominator. Okay, so tan square is in the denominator actually. Okay, so by tan square theta. Okay, so tan square is in the denominator, so let us write tan square in the denominator. So 3 by 4 d square k by tan square theta into integration of dt is t square by 2. So if you substitute the limits, you will get t square by 2 is equal to h cube. So what is the expression for h from this expression? Height at any time t is given by 3 by 8, because 2 4s are 8, 3 by 8 d square, or you can write k first, k times of d square t square. This 1 by tan square can be written as cot square theta times this whole value whole to the power 1 by 3 is the total height at any given time in the tank. Okay, so the total height at any given time in the conical tank is given by height at any time is given by this value, which is 3 by 8 times of k d square t square cot square theta whole to the power 1 by 3. Okay, so if you check the options, first of all, this is wrong, 5 by 8 is there, this is 3 by 8 but power is 1 by 8, but tan square theta is in multiplication, wrong. So this is not power 2 by 3. So this is the correct option, which is height of the tank at any given location at any given time is basically given by 3 by 8 k t square d square cot square theta whole to the power 1 by 3. Clear? So please type in the chat box, is this clear to all of you? It's a very simple question, just some 2-3 lines. Okay, 2-3 lines you need to do, but you need to write the things little carefully. Okay, you face problems to get control volume. Look, basically this is the volume that we have taken, because this is the volume of interest at height h. This actually increases. Okay, so in tomorrow's class we'll talk about control volume analysis. Okay, they will take a lot of control volumes. We will talk about basically this linear momentum equations, angular momentum equations, all these things. So at that we will show you how to clearly identify the control volumes. Okay, clear? But did you all understand this question? These are general type of questions. Normally some fluid is going, then definitely what happens, height increases. So they are telling you for some velocity what is the height increase. That's it. Okay, so simple question, 2 to 3 lines that we have done. We identified these two quantities, then done some integration. That's it. Clear? Okay, how many of you like this question? Please tell me. How many of you feel that this is a very good question? Simple application. Okay, normally if you have a tank, water is flowing, what is the height is? Okay, so we have done the same thing, same analysis. Okay, great. So let's go for the next question. Okay, so I hope you enjoyed this question. It's a very good question actually. Okay, because many times they can ask you some expressions, h cube t square, all these things. Okay, by giving some time t, all these things. Okay, Chandan Sharma, what is this folding hand implies? You are liking this question? Great. Okay, yes, practical kind of questions. Okay, means practically what's in yesterday's case also we have seen buoyancy. Whenever some stick is floating, what is the angle at which it floats? All these kind of questions. You need to convert this physical things, physical phenomena that's happening into mathematical equations, and you need to solve for solutions. That's it. Clear? And if you are liking these questions, then please do like. Okay, we'll have more questions like this. Okay, now let's go for the next question. So see here, an incompressible fluid flows past a impermeable flat plate. So there is some figure which is given. So this is impermeable flat plate. Impermeable flat plate. Okay, so this is impermeable flat plate. Okay, so now if you see, if this is impermeable flat plate, then as shown in figure, with a uniform inlet profile, U is equal to U naught. So at the inlet, means at the inlet of the pipe, at the inlet of this, at the inlet section. So if you take this inlet section, then what's happening? This is the inlet. So this is inlet, and of course if you see at the inlet section, the velocity is uniform, it is equal to u naught. So if you see u is equal to u naught equally, means if you take these points, at all these points the velocity is u naught, u is equal to u naught. Okay, then once the flow started, then definitely you know obviously what happens because of the viscosity and all these things, then the velocity of the layers will come down. Okay, I didn't explain you in clear way because we are not dealing theory, we are explaining only questions. But if you see there is some velocity which is called the no slip conditions we have talked, and if you see as this fluid moves like this, then definitely if you see when this fluid moves in this direction, then definitely the flow velocity at this bottom layer comes to 0, and the slowly it applies brakes on all the layers. Okay, so if you see this is how the velocity profile at the outlet, means at some different section. So they are asking you, and a cubic polynomial exit profile. So if you see the velocity profile at the exit is some cubic polynomial which is given by some relation u naught into 3 eta minus something. Okay, the volume flow at q across the top surface of the control volume is dash, means they are asking you if this is the top surface of the control volume, if this is the top surface of the control volume basically, then what is the velocity, what is the discharge to this top surface of the control volume. So if you have this control volume and if you have a top surface, then we actually our point of interest is to calculate what is this q. Okay, so let us calculate how to calculate this q. Okay, Aditya, can you take session on Navier-Stokes equation? Yeah, I can take, but let us, once this Abhyas gets finished, then if required we'll take some topics. Anyhow, crash course will happen for fluid mechanics, then definitely you can work out. Okay, so now powerful, let's, very good. So if you see, first of all, if you take this control volume, they have directly given you this control volume this time in question itself. So if you see, this is the control volume, this is the control volume, they have directly given you in the question. So if this is the control volume, then please tell me, first of all, if this is the case, if you write mass flow rate into the control volume minus mass flow rate out of the control volume is equal to rate of change of mass inside the control volume, correct? Now please tell me this, let us try to understand one thing. Let us suppose, if you see, this is the only phase through which mass is flowing in, correct? And obviously this is impermeable flat plate, means this plate cannot allow any fluid to flow it. So definitely the discharge along this phase is 0. Let us name these points A, B, C, D for example. Then you know discharge along this phase AD is 0 because this is quietly closed. Now if you see, this gap is given delta, because if you see this line equation is y is equal to delta and this is y is equal to 0. So delta is some thickness which we don't know, it's just some geometrical thing. Delta is the height of the plate, okay, height of the flow for example. Okay, so they are asking you what is this velocity that is going out from this phase. Okay, so let us see what is this value of q. QBC is how much? This is what they are asking you. Okay, what is the value of QBC? Okay, so let us see how we will calculate this. So tell me one thing, if you have some flow like this, can the plate hold some fluid in this? Means can the plate store some fluid in this, or whatever is coming in that should go out? Definitely, please tell me. Here there is no empty space, the flow, that the space above the plate is having some flow, so it cannot be like in this volume some fluid can stay there for some time or some fluid can excessively go, correct? Means if you take this is the control volume, then definitely the rate of change of mass inside the control volume is 0. Yes or no? Correct, because within that control volume you cannot have any mass getting stored there. At the same time you also cannot have any mass which is leaving in excess, means you cannot create some vacuum here. Okay, how discharge is 0? Because there is no flow in the plate in the downward direction. From the, look, whenever there is some flow above the plate, from this plate you cannot have any discharge. Okay, through the plate you cannot feel some fluid coming down. Okay, so that's why. Now if you see mass flow that is coming in, that should be equal to mass flow that is going out. So what are the phases through which mass is coming in? Rho into discharge to AB. This is the only phase which is mass coming in. So this is equal to mass going out QBC plus discharge to CD. Okay, so this is the case because discharge to AD is 0. Okay, discharge to CD is actually 0. Now if you see density, let us cancel. If you cancel this density, discharge is nothing but How you calculate this discharge means basically you want this expression QBC. So QBC is actually equal to discharge to AB minus discharge to CD. Okay. Now let us see how we will calculate this discharge to AB and discharge to CD. Okay. Now if you see discharge, how you calculate this discharge? Look, let us suppose if you have a section. At this section, if velocity is changing, something like this. Okay. So if you see some velocity is changing like this. This velocity is changing with respect to y. Velocity is changing with respect to y. So whenever velocity is changing with respect to y, then definitely if you want to calculate the discharge, means try to understand there is a plate like this. Okay. Means in the side view, if you see, in the side view, if you see, so in the side view, you have a rectangular plate. Yes or no? Because if you see, there is some width of this plate, means this plate which is here will have some width, at the same time there is some height. So the velocity is increasing. So if you want to calculate the discharge, means the velocity is in this direction perpendicular to this plane. So if you want to calculate the discharge, how will you calculate? Look, you take the small discharge that is passing through this small height dy, for example. Okay. If this is dy, means correspondingly, if you have this section, so if you have this section, for example, if this height is dy, then if you see the area, if this is width of the plate w, if this is width of the plate w, for example, how you actually calculate the discharge? Discharge is area of cross section into flow velocity. So let us suppose small u is the velocity of the flow through this cross section, then this area available for the flow is w into dy. Okay. So this is the area available for the flow, and the velocity perpendicular to this area is u. Let us suppose at this location the velocity is u. Then the small discharge that is passing through this section is u times of w into dy. So if you see, if you integrate this, u into what is the thickness of the plate? Width of the plate is given. Width of the plate is b. Nothing is given, but how this b? What is this b? Okay. So if you see, control volume is there, u naught is there, flow at an impermeable plate. Okay. So width of the plate is b. Let us take this. Okay. Width of the plate is b. Width of the plate is actually b. Okay. So whenever width of the plate is b, you can write u into b times of dy from integral 0 to delta minus across CD u times of b dy 0 to delta. Now what is the velocity profile at AB and what is the velocity profile at CD? Let us see here. So velocity profile at AB is uniform. So u is equal to u naught at all the heights. Okay. So this implies, if you see integral 0 to delta, this u is actually a constant function here. U is equal to u naught. So u is equal to u naught means u naught b dy minus integral 0 to delta. So what is the velocity profile at CD? U at CD is given by this function at the exit. U at CD is equal to u naught times by 2, 3 times of this complete values. Okay. So if you see u naught by 2 times 3 eta means 3 y by delta minus eta cube. So y by delta whole cube. So y cube by delta cube within the limits b to dy. So this is the difference in the discharge between these two sections. Okay. So here it's a uniformly velocity profile, but here at CD this is having some different form. Okay. So now if you simplify this result, you will get the answer. Okay. So let us simplify that result. Let me take one new slide. So let us see, if you take this new slide, then discharge to BC. Discharge to BC is equal to, now what about the value of this integration? U naught is constant, b is constant. So integral dy from 0 to delta gives you delta u naught b delta minus, here u naught by 2 is constant, u naught b by 2 if you take out, u naught b by 2 if you take out integral 0 to delta, this value 3y by delta minus y cube by delta cube times dy. So this is the differences in the discharges. Okay. So now if you simplify this result, you have u naught times b delta minus u naught b by 2 times, if you simplify this, y square by 2 delta square is what? So you have 3 by 2 times of delta minus delta by 4 if you simplify this. Okay, so this is what you have. Okay, if you simplify this integration, 3 by delta times y square by 2, so 3 by 2, 1 delta, delta square minus 0, so 3 by 2 delta minus. Similarly here if you simplify, you will get delta by 4, some integration, mathematical integration if you do. So u naught b delta minus u naught b by 2 into, what is this value? If you multiply 2 and 2 here, 6 delta minus delta, so 5 delta by 4 is what you have. So 5 delta by 8, so total if you simplify, 3 by 8 times of u naught b delta is what you have here. So this is the discharge to the phase BC. So is this clear to all of you? Did you all understand how did we get this discharge value? The only thing is it's very simple. If this is the function, I told you how to calculate the discharge, how to write the discharges when velocity profile is changing. Okay, so when velocity profile is changing, you take a small thickness dy and then you do the integration u into w into dy. Okay, so at section CD, okay, CD, if we calculate the discharge by area and cubic velocity profile, will it give the discharge? Yes, that's what we have done. We have calculated using velocity profile into this value. Okay, area into cubic velocity cannot multiply, because if you see, all these points have different velocities, different values of y. Okay, because if you see, if you take this as y axis for example, all these points have different values of y. Okay, when values of y are different, then definitely this u will be different at different points. Okay, that's why we need to go for integration. Clear? Did you all understand why we need to go for integration? Because at different points on this section, the value of y is different. So when value of y is different, the velocities are different. So you cannot directly multiply area with velocity at some point. Okay, clear? So is this clear to you? We'll take the velocity profile at AB into b dy. Since u is constant, we have replaced it with u naught. Here this ucd is not constant, you have some function, so you replace it with that. Clear? Mass conservation, basically you see, mass conservation, we have applied discharges and we have calculated what is the discharge from this phase BC. Yes or no? So please type in the chat box. Is this clear to you? So please type in the chat box. Yes or no? Yes? Clear? So basically, normally many of you are afraid of this concepts called boundary layer theory, all these things, but everything, if you apply mass conservations, momentum conservations, easily you will get answers. Okay, let us suppose if I talk about this using displacement thickness, boundary layer thickness, all these things, you will definitely get, you know, something not very comfortable. But if you see, this is just some thickness delta and we have done some analysis, that's it. Okay, okay, clear? So our job is to make the things simple and of course again matching the questions with gate level. Clear? Okay, now let's go for the next question. So there is this question: the axial velocity profile in a pipe of radius r is given by the equation u is equal to um times 1 minus small r by capital R whole power n, where um is the maximum velocity at radius r is equal to capital R. Okay, so sorry, at radius r is equal to 0, because if it is maximum, then this is radius r is equal to 0. For n is equal to 1 by 5, the value of average velocity of the flow is given by u average is equal to k times of u times um. The value of k is dash. So one thing, so why discharge at section AB is minus section at CD, minus section at CD. So see here, whatever the discharge is coming in, this discharge should be equal to discharge to this phase plus discharge to this phase. Okay, so that's why we have it in this equation. So from this equation we got this, BC is equal to AB minus CD. Okay, no, section CD cannot give the integration, because you know, look, one thing, I'll ask you one question, so please tell me. Here every particle has some high velocity, every particle has some high velocity, u naught, but coming to here, this particle has 0 velocity, this particle has 0 velocity, this has some less velocities. Okay, so because you see, by the time this is coming to u naught, this is also u naught, but the velocities at these points are not u naught. Okay, so the velocities at these sections are less than u naught. So whenever areas are same, but at this section, if velocities are low, then can you please tell me, will the discharge be same at these 2 points? At these two sections, actually, if you calculate the discharge, please tell me, will the discharge be same? Because for the same area, velocity at the points is less actually. So that's why that decreasing part of discharge which is there is actually leaving to this phase BC. Clear? We have actually applied continuity for the section. Losses and all is there, but right now there is no loss in the mass actually. Mass is always conserved. Clear? There is loss of momentum and all, but that is not the case. Okay? It won't be? Yes, there will be different discharges. Okay, so that's why this discharge, what is coming here, should pass through these two phases actually. Okay? No mass accumulation, so that's why this control volume mass is, rate of change of this control volume mass is actually 0. Clear? Now, if you see, this is in Cartesian coordinate systems, means if you have xy coordinates, this is how you have your dy and x. Now, let us suppose if you see this example. Okay, what is the answer for this question? I forgot. 3 by 8 times of this value. So, 3 by 8 times of u naught b delta. Okay, so 5 by 6 is given. I think answer has to be, it is changed, but 3 by 8 u naught b delta is correct answer. Okay, so 3 by 8 u naught b delta is, I think he has forgot to change the answer. B is the correct answer. Okay, B is the correct answer. Okay, fine. Yes, displacement concept derivation and all. Yes, of course. Okay, they will get this delta. Fine. Okay, anyhow, so let's go for the next question quickly. So see here, this question, the axial velocity profile in a pipe of radius capital R is given by the equation u is equal to um into 1 minus small r by capital R whole power n, where um is the maximum velocity at r is equal to 0. For n is equal to 1 by 5, the value of average velocity of the flow is given by u average is equal to k times of um. The value of k is dash. Okay, so let us see here. There is a pipe. There is a pipe. There is a pipe like this. Okay, so whenever there is a pipe with some axis, there is some axis for this. Okay, so whenever there is some axis, they have given you, if you measure this radius, because radius is always measured from the center, so if you measure this as the radial direction, they are asking you, they have given you some velocity profile here. Okay, so if you see the velocity profile in a pipe generally looks like this. Okay, so the velocity profile in a pipe looks like this. From the center, from 0 location, it slowly increases and it reaches maximum at the radius. Similarly, this is also symmetric, so it happens to be like this. So this is the velocity profile. Okay, so if this is the velocity profile, then how you calculate the velocities? See here. So now, if you see the side view of this pipe, you have certain, circular shape actually like this. Okay, so you have certain circular shape. Okay, now if you see in Cartesian coordinates, we have taken it like this. Okay, so if you see, we have taken the velocity in this direction. So whenever there is a velocity change, we have in the y direction. If there is a velocity profile, this is the area for the discharge. But now if you see this case, if you want to take at some small radius value, means let us suppose if you want to take a small section here, if you want to take a small section here, then how it comes out? It comes out to be a small area in this. Okay, so at some radius r, you have some, at some small radius r, if you see, at some small radius smaller, and let us suppose this is smaller value. Okay, so means basically if I enlarge this diagram, if you see, you have this center and you are taking some small elemental area. Okay, so you are taking some small elemental area from this center. So this radius is smaller and this is dr. Okay, so this is dr and this is the small elemental area in a pipe at some radius. Okay, so if you see, this is the small elemental area. Okay, so if this is small elemental area dA, if this is small elemental area dA, then what is the value of this dA? dA is nothing but 2 pi small r times dr, correct? Which you can see very easily that this area is 2 pi small r times dr. Now, if you want to see how to calculate the average velocity, what is the concept of average velocity? Look, I'll tell you. Normally, with radius, the pipe velocity, the flow velocity changes in the pipe. Okay. Now, if you assume this complete section is having same uniform velocity means if every particle is moving at equal velocity. Okay, if every particle is moving at equal velocity, but which is not actually the case, of course. Here if you see, the velocity will be something like this. Okay, but if you assume that at every location the velocity of the particles is same, then the velocity for the same cross section you have the same amount of discharge. Means, try to understand here. Normally, because of this velocity profile, through this pipe of radius capital R, you have some discharge. Now, let us suppose for the same area of cross section of pipe, means for the same pi r square, if u average is the velocity at any section, then the discharge should be same as in the original case. Clear? So that's how we define the average velocity. Means actual q is how much? Actual q is equal to integral u with respect to radius into 2 pi r dr. This is the actual discharge from r is equal to 0 to r is equal to capital R. Now, when you assume uniform velocity, that means this discharge value should be same as u average into pi r square. Did you all understand what is the concept of u average velocity? Average velocity is that velocity which, when you assume the velocity is same at every point, at every radius, this for the same cross section of the flow, the average velocity gives you same discharge for this actual discharge. Clear? किसी भी शेप के लिए वैलिड होगा ना? Yes, for any shape, definitely. Okay, so now this is the concept of average velocity. Means the discharge what you have calculated using actual velocity profile, that should be same as this discharge for the average velocity through the same pipe. Okay, so this is the concept of average velocity. Now, once you understand this concept, let us see. This relation is given. Integral r is equal to 0 to capital R. What is the velocity at any given radius? Um into 1 minus r by r whole to the power n into 2 pi smaller dr. This value is equal to u average into pi r square is what you have. Okay, so now if you simplify this pi and pi here, now let us see what happens here. Um into 2 is also there, 2 times of um into integral r is equal to 0 to capital R 1 minus small r by capital R whole power n times r into dr is equal to r square times of u average. This is the equation. Now, in this equation, the only thing that you need to calculate is this integration. Okay, why I have given you this integration is, this is one special type of integration, and normally many students they face issues when trying to calculate this integration. Okay, many students will come till this point, but they are not able to calculate the integration of this value. Even many of you might have started attempting this, but you are facing issues with this integration, correct? How many of you faced issues with this integration? Please tell me honestly. You have started the question, you came till this point, but facing problem with this integration. How many of you are facing this? Please type in the chat box. I hope definitely at least there will be some 2-3 students who are facing issues out of these many, who are feeling it difficult to do this integration. Okay, so look, let us see how we are actually facing this integration. Okay, so how we actually do this integration is, let us see how we'll actually do that integration. So integral r is equal to 0 to capital R 1 minus small r by capital R whole power n into r times of dr. Okay, so how will you do this? Let 1 minus small r by capital R is equal to t. So this gives you r is equal to capital R times of 1 minus t from this equation. Okay, so let us suppose you make this substitution. Okay, if you make this substitution, yes, see, Amit faced issues, Chandan, Raushan, all of you are generally facing issues. I understand, because this is one peculiar integral which we see in turbulent flows also. This kind of integration is slightly complicated to evolve. Okay, but of course, if you have some good knowledge on mathematics, just by doing this substitution, you can get these values. Okay, so if you see, so this is the equation, because if you take this bracketed term as t, then if you see 1 minus small t is equal to small r by capital R, so small r is equal to capital R times of 1 minus t. If you differentiate on both sides, the radius is constant, differentiation of 1 is 0 minus dt. This is what you have. Lower limit. So what is the lower limit? Normally in definite integrals, when you substitute some substitution, definitely limits also change. So lower limit. What is the lower limit? 1 minus r by r is equal to t. So tell me, what is the lower limit when variable is r? When variable is r, lower limit is 0. So 1 minus 0 by capital R is equal to t, which implies t is equal to 1. Next, upper limit. 1 minus small r by capital R is equal to t. This is the substitution. And in case of small r, the upper limit value is r is equal to capital R. So capital R by capital R, this is equal to t. So this implies t is equal to 0. Okay. So now if you substitute these 4 results, substitution, dr value, lower and upper limits in this integration, this integration turns out to be r means t is equal to 1 because the lower limit is t is equal to 1, upper limit is t is equal to 0, t power n into capital R times of 1 minus t into minus dt. This is the integration value. Now using this minus sign, if you flip these two integrals, then this gives you t is equal to 0 to t is equal to 1. This capital R is constant anyhow, capital R into, sorry, one more capital R is there, r times of minus dt. So r square if you take out, you have t power n into 1 minus t times dt. This is the integration value. Now it's very easy. If you multiply t power n minus t to the power n plus 1. So if you simplify this, r square into integral 0 to 1 t power n minus t to the power n plus 1 dt. This is the integration. Okay. So if you simplify this, r square times of t power n plus 1 by t n plus 1 minus t power n plus 2 by n plus 2 within the limits 0 to 1. So when you substitute 1 here, r square times of 1 by n plus 1 minus 1 by n plus 2 is what you have, and when you substitute zeros, this is 0. So now if you take the LCM, you will get r square by n plus 1 into n plus 2. This is the value of this integration. Okay, so the value of this integration is r square by n plus 1 into n plus 2. So this integration, this is completely mathematics, but calculating that integral value is slightly important for you. That's why I have given you this question, and once or twice it came in GATE examination also. In XC it came exclusively. Okay, so now if you see this if you substitute now, 2 times of um into r square by n plus 1 into n plus 2 is equal to r square times of u average. Okay, so if you cancel this r square and r square, so radius of the pipe don't have any importance here. So u average is equal to 2 times of um divided by, what is the n value they have given in the question? N value is basically 1 by 5. Normally in turbulent flows and all, you have 1 by 7. So when you use 1 by 7, you will get this value something different. Okay, I'll show you what is that value also. Okay, so see here, 2 times of um divided by 1 by 5 plus 1, 1 by 5 plus 1, total 6 by 5 into 1 by 5 plus 2. 1 by 5 plus 2 is how much? 11 by 5. 11 by 5. So if you simplify this 2 cancels this 3 times, and if it goes up, 25 by 33 times um. So whenever this u average, if you see, u average value is actually equal to 25 by 33 times um is what you actually have. Okay, so this is the constant value. Now let us suppose if n value is 1 by 7. Okay, so let us suppose if you keep n value as 1 by 7, then this gives 8 by 7, and here it gives you 1 by 7 plus 2 is 15 by 7. Okay, so if you see 2 table, if you cancel here, you will get 49 by 60. That is one very important case. When n is equal to 1 by 7, k value is 49 by 60. Many times this 49 by 60 value is, asked sometimes, so that's why you can remember this. Okay, but anyhow, for this question, this value is 25 by 33. Okay, so let us see what is this value. 25 by 33, 0.757, 0.757, round off to 2 decimal places, so 0.76. So 0.76 is in between this 0.74 to 0.77. Okay, so here 2 important things you need to observe very carefully. If n is equal to 1 by 5, I am giving you the values, so please take this. Okay, so k value is 25 by 33, and when n is equal to 1 by 7, which is the most general case, because you see in turbulent flows and all, we go for this 1 by 7th model. So k value in that case is 49 by 60 is what you have there. Okay, so for n is equal to 1.5, this k value is 0.76. Of course, mass conservation, but the concept of average velocity is important here. Okay, fine. So please type in the chat box. Is this clear to all of you? Yes or no? So type in the chat box. Is this clear to all of you here? Chandan, okay. So think you put the limits reciprocal because I have changed this minus sign. Okay, I have used this minus sign. I have used this minus sign to interchange the limits. Okay. No, Chandan, to remove minus. Okay, you're answering him basically. Okay, great. Okay, so let's go for the next question quickly. So this is next question. A circular pipe 10 centimeters in diameter has a 2 meters length, which is porous. In this porous section, the velocity of exit is known to be constant. If the velocities at the inlet and outlet of the porous section are 2 meters per second and 1.2 meters per second, the average velocity of this emitted discharge is dash meters per second. Look, let me tell you. There's a pipe like this. There's a pipe like this, okay, and given it is a porous pipe. What is the meaning of porous pipe? Look, I'll tell you. So if this is a pipe, now the meaning of porous pipe is what? Normally if you have a pipe, what does it do? It just transfers fluid from this point to that location. But whenever the pipe is porous, porous means small holes. Okay, you might have seen this word called porous plug and all these things. So porous means like sponge kind of thing. Basically it has some holes. Okay, so because of this pores, what's happening here? There is some velocity which is going out. Okay, there is some flow which is actually escaping this pipe. Okay, because of the porosity of the pipe. Okay, so the pipe obviously have some holes. So because of this, there is some fluid which is escaping out. All over the circumference there is some holes. So because of which fluid is actually escaping out. Okay, like this. Similarly in the bottom direction also, because means all over the 360 degrees there is some escaping of the fluid outside. Okay, so some fluid is actually escaping like this. Right? Okay. So there is some fluid which is escaping here. Okay. Okay, so there is some fluid which is escaping here. Okay, now whenever there is certain fluid escaping here, try to tell me this. Let us suppose if some discharge is moving inside Q, and let us suppose out we are getting only Q1 discharge. Okay, Q1 we are getting outside discharge. Then definitely the emitted discharge is how much? Let us suppose if you call this emitted discharge as QE from all over the circumference, means try to understand inside there is a fluid which is flowing, but this pipe has small pores all over the 360 degrees. So because of that some water is coming out of the pipe from all the 360 degrees like this. Okay, so now if you see Q is equal to Q1 plus QE. Okay, now what is Q? Q is nothing but pi by 4 d square at inlet into velocity at inlet. Correct? Means if this velocity at inlet is V in, then if the cross section is pi by 4 d in square, this is what you have. This is equal to Q1. What is the leaving? Pi by 4 d out square into V out plus. Now what is the emitted discharge? If you want to calculate the emitted discharge, they are asking anyhow average velocity. So let us suppose at every location the velocity is VE. Escape velocity is VE. Okay, emitted velocity is VE all over the length. If this length is L, then tell me for this emittance, if fluid is coming all over the surface of the pipe, can you tell me what is the area available for the fluid to come out along the surface? All the surface area is available for the fluid to come out. So can you tell me for the fluid coming out radially in all the directions, can you please tell me what is the velocity that is available, what is the area that is available for the emittance? So please type in the chat box what is the area that is available for the fluid to come out actually. 2 pi RL, which is nothing but pi dl. Correct? Means if you have a pipe, the total surface area of the pipe is available for the flow. So surface area of the pipe is pi d is the circumference multiplied with this length L. Okay, so pi dl is the area available for the escape. So pi d into L. Okay, so let us see, plus VE into pi dl, length of the pipe. Okay, now definitely you see this is a uniform pipe, so d in, d out and d, all these are the same diameter of the pipe. Okay, so if you substitute here pi by 4 d square into velocity at inlet minus pi by 4 d square into velocity at outlet is equal to pi dl times this emitting velocity. Okay, VE. So if you simplify the things, pi gets cancelled, 1d gets cancelled, so this implies VE is equal to d by 4L times of V in minus V out. This is the expression. Okay, so if you simplify, I think all the values are given directly. So if you simplify here, d, diameter of the pipe. So what is the diameter of the pipe here? The pipe has 10 centimeters diameter, means 10 to the power minus 1 meters, into by 4 times of length. So what is length here? Length of the pipe is 2 meters, so it has 2 meters length. So it has 2 meters length multiplied with V in minus V out. So V in at the inlet is 22 meters per second, and at the outlet it is 1.2 meters per second. So 2 minus 1.2. So this is what you have. So if you simplify this, 10 power minus 1 into 2 minus 1.2, 0.8. So 8 into 10 power minus 1 divided by 2 4s are 8. So this 8 gets cancelled. So 10 power minus 2 meters per second, which means 0.01 meters per second is the emittance velocity through which this fluid is going out of the pipe. Clear? So is this clear to all of you? So please type in the chat box. Yes, I'm happy that many of you got 0.01. The main point of understanding here is what is the area available for the escaping fluid. Okay, so for the fluid to escape radially, the total surface area is the available area for the flow. So that's why we have multiplied a pi dl here. Clear? So it is basically 0.01, which is in this range. So 0.01. So that's why the range is from 0.008 to 0.012. Okay, clear? So this is how we have this question. Okay, it's simple question again. Okay, now let's go for the next question. So let's go for the next question quickly. So for a 3-dimensional velocity field described by V is equal to V bar. Okay, so this is a velocity vector. So V bar is equal to y square plus z square times I. Of course, bold letters means this is I bar, J bar and K bar. The components of rotation is. It's a simple question. Just I thought of giving you to make you know how to calculate the angular velocity components. Okay, so let us write the velocity vector. So if you write the velocity vector, V bar is equal to y square plus z square times I bar plus x square plus z square times J bar plus x square plus y square times K bar. So this is the velocity vector. So if you want angular velocity vector, you know this is half times of curl V. Okay, so which means angular velocity vector, let us suppose if you take omega xi plus omega yj plus omega zk, then this is equal to half times of curl V, which is I j k dou by dou x dou by dou y dou by dou z u y square plus z square. This is x square plus z square, and here it is x square plus y square. So this is the velocity vector. So this is half times of I bar into so now I bar into dou by dou y of this quantity 2y minus dou by dou z of this quantity, which is 2z, minus j bar times of dou by dou x of this quantity 2x minus dou by dou z of this quantity is 2z, plus k bar times of dou by dou x of this quantity, which is 2x, minus dou by dou y of this quantity is 2y. So this is what you have. Now if you see carefully, this is 2 in every term can be take common and it can be cancelled with this 2. Okay, so if you see, okay, so if you think it, we can see I bar times of y minus z. We are writing a plus sign here, so let us make plus. If you make plus here, this turns out to z minus x, plus k bar times of x minus y. Means if you see the values, this omega x is given by y minus z, this omega y is given by z minus x, and omega z component is given by x minus y actually here. Okay, because if you see, we are taking the points. Okay, so location, what is the location at which they are asking you? Again, location is missed. Location, these people are missing always. Okay, fine, let 1 comma 2 comma 3, let us say. Okay, I hope this is the value. So at 1 comma 2 comma 3, so at 1 2 3, omega x is equal to y minus z. So y minus z, 2 minus 3 is minus 1 radians per second. Omega y is how much? Omega y is 3 minus 1, so 2 radians per second. Omega z is 1 minus 2, again minus 1 radians per second. Okay, so minus 1 2 minus 1, so if you see, minus 1 2 minus 1, so B is the correct answer in this case. Okay, so the components of rotation, so B is the correct answer in this case. Okay, so B is correct answer, but please make sure whenever you are writing this, because you are taking a plus sign here, you need to make a plus sign when writing these components. Okay, you need to mention this components. Okay, you need to mention this plus sign because you are assuming a plus sign. If for example, if you miss this, then definitely you see this minus 2, or definitely they would have given one option C, minus 1 minus 2 minus 1. This is the option which is just having a change with this minus sign. So if you forget this adjustment as plus, because there is a plus sign here, that's it, you will get a minus 2. Clear? So you should be very careful when writing the angular velocity vectors. This is one simple question which I have given you so that you can calculate the angular velocities. Similarly, for shear strain rates and all, you have the expressions. Okay, so if you quickly want me to give you, let me give you this. Let me give you this value. Let us suppose if V is equal to, I'll give you these values, so please keep these values with you. Okay, they will be helpful to you. Ui plus Vj plus Wk if you have, then definitely linear strain rates is given by linear strain rate in x direction is given by dou u by dou x. Of course, if there is some time, I have derived these things, dou u by dou x and all, but again the derivations are slightly involves trigonometrical involvement, so that's why I'm just giving you values. Okay, so please keep this. Definitely when in short crash course, Amit Dixit sir will take over this, but normally these are the values which can easily derive when you take functions as u of x, v of y, and if you do some Taylor series analysis, you will easily get this. Okay, so e of x, strain rate in y direction, dou v by dou y, strain rate in z direction, dou w by dou z. This is the linear strain rates. Okay, shear strain rates, or rate of shear deformations. Okay, sometimes it's also called rate of shear deformations, or this, if you call this, then shear strain rate in the xy plane is given by dou v by dou x plus dou u by dou y. Similarly, gamma in yz plane is given by dou v by dou z plus dou w by dou y. Shear strain rate in xz direction is given by dou u by dou z plus dou v w by dou x. These are the components. Similarly, you know how to calculate angular velocity. Okay, just take the curl of the given velocity vector, you will get the angular velocity. Clear? Normally these expressions are sometimes important. They'll give you velocity profile and they'll ask you these values. So once you get the values in terms of x comma y, just substitute the points, you will get the answers. Okay, clear to all of you? Okay, I'm not deriving this because this is just a question series course, so I'm just giving you the values directly. Okay, fine. So let's solve one last question before we leave. Okay, yeah, I think there is one last question. Fine. So if you see, there is one last question here. So see here, a flow is described with a stream function psi is equal to 2 times of square root of the xy. The point at which the velocity vector has a magnitude of 4 units and makes an angle of 150 degrees with x axis. So see here, there is some xy coordinate system. So whenever there is certain xy coordinate system, they are asking you for the points, means basically they are asking you for the point where the velocity, means if you take any point on this, they are telling you the velocity should be in this direction, something like this. Okay, the velocity should be in this direction, such that if this is your v, magnitude of this velocity is 4 units and the angle made with x-axis means basically this angle is 150 degrees. This is 150 degrees. Okay, so they are asking you what is the point, and the stream function in this flow is given by psi is equal to 2 the xy. So they are asking you the point at which magnitude of this velocity vector. So first of all, tell me, if you have a stream function, the u means if this velocity vector is ui plus bj, for which the stream function is given by this, then these are related by u is equal to dou psi by dou y and v is equal to minus dou psi by dou x. These are the relations. Okay, so because if you see phi and psi are actually satisfying Cauchy-Riemann equations, this is how you have this. Okay, so u is equal to, so this is given, how much is this function given? 2 times of square root of 3 into xy. So 2 times of root 3 into xy. So u is equal to, if you differentiate this with respect to y partially, you have 2 root 3 x. Similarly, v is equal to minus 2 root 3 y. So u component is this and v component is minus 2 root 3 y actually here. So if you see, if you have a velocity like this, so if you resolve this into x and y components, for example, if you have x component and y component like this, v and u, for example, v and u, this is u and this is v. If this angle is theta, then how will you get this? If this is v, capital V, for example, if this is small v, then you know magnitude of v is equal to root of u square plus this component v square. Okay, if you take this velocity vector v, for example, magnitude of this v is this much, and theta can be identified by tan inverse of v by u. Correct? It's a simple question. So tan inverse of v by u. But just to calculate this values u comma v, you need to calculate this stream function. Using from the stream function, you need to calculate this. So if you simplify these expressions, then you know magnitude of v is equal to 4 units. So this implies a root of 2 root 3 x whole square plus 2 root 3 y whole square. This is equal to 4, which means you can understand x square plus y square means at this point, at this location, if you take this point as x comma y, then x square plus y square is equal to 4 square is 16 and this value is 12. So total 4 by 3. So x square plus y square value is 4 by 3. Okay, next coming to this value, tan theta. So theta is 150. So tan theta is minus 1 by root 3. Okay, so tan 150 is nothing but tan 180 minus 30. So minus 1 by root 3 is equal to v minus 2 root 3 y divided by 2 root 3 x u component. Okay, so if you simplify them, 2 root 3 gets cancelled, this minus and minus gets cancelled, so you can write x is equal to root 3 times of y. Okay, so x is equal to square root 3 times of y here. Okay, so x is equal to square root 3 times of y. So if you replace here root 3 y whole square plus y square, so 4 y square is equal to 4 by 3 is what you have. Correct? So tan 150. So tan 150 degrees is how much basically? So tan 150 is tan 180 minus 30. So tan minus tan 30, which is 1 by root 3. So 1 by root 3 is equal to y by x. So y x is equal to root 3 times of y. So if x is equal to root 3 times of y, then 4y square is equal to 4 by 3. So y is equal to 1 by root 3 is what you have here. Okay, so y is equal to 1 by root 3. So let us check the options in which y is equal to 1 by root 3. Oh, all 4 options have this. Y is equal to 1 by root 3. So if y equal to 1 by root 3, then definitely x is equal to 1. X is equal to 1. Okay, so y is equal to 1 by root 3 means x is equal to 1. So the coordinates are 1 comma 1 by square root of 3 actually. Okay, so x value is 1 and y value is 1 by root 3. Okay, so I think maybe they have interchanged the coordinates here. This is 1 actually, option C should be correct answer. This is 1 and this is 0.577 because 1 by root 3 is 0.577. So C is the correct answer. Okay, because you see clearly this is the analysis. It's a simple analysis, but obviously to get the values of u comma v, you need to calculate this using this magnitude of velocity and of course the angles. Okay, clear? So please type in the chat box, is this clear to you? So C is the correct answer. The coordinates has to be interchanged. The x coordinate is 1 and y coordinate is 1 by root 3. Okay, fine, clear? So this point where you have this is 1 comma 1 by root 3 is the point where this velocity for this particular stream function has this velocity values. Clear? Yes? Okay. So I think yes, we have a beautiful team for mechanical and XE. So you see, all of us had some, we had a very great variety of team. Actually, if you see, every one of us has a very individual, very much exposure to this teaching and all, and all of us, many of us have some industry experience. You see, Swadesh Kumar Singh sir, Vinod Dachil sir, working with INA and all, Negi sir, Apoop sir, everyone, Amit Dikshit sir, of course. If you see, we have a very good team, and definitely we are bringing you this Abhyas series such that the questions which are discussed in this Abhyas series, if you are thorough with all the questions, definitely you will have all the knowledge for attempting the questions of GATE 2023. Okay, so if you see, for example, the most scoring sections of GATE examination, maths plus aptitude, myself plus Ratan sir, of Hindi batches, Vishal Soni sir, and this, Amulya Ratan sir, and coming to technicality, Damal, coming to my domain, Negi sir, myself, and Sandeep Chandrakar sir. So we are dealing this Damal part, okay, and coming to design, Apoop sir, theory of machines by Vishwajit, we have all these persons. Okay, so we have a very good team, and we are putting all our best efforts to bring you the best content and the best questions that can be possibly discussed in this GATE Abhyas series. Okay, math will start soon. We are going to give a very good start for maths very soon, and of course some of you are asking for this Gateopedia very soon. Within a week's time you are going to get your material for free. Okay, so don't worry, and definitely we are putting our best efforts to make in each and everything to make you have all the things ready for the GATE 2023 exam. Okay, so please, sir, launch GATE test series mechanical. Yes, we are about to launch the test series also. Hopefully within a couple of weeks time you will be coming to know of the complete schedule. Okay, so are you all liking the sessions? So please type in the chat box, are you all liking the type of questions that's being discussed here, and are you all liking the sessions? Yes, maths हम start कर दी क्या? Yeah, we'll start maths. Okay, no issues. We'll start maths very soon, and of course we'll yes, if possible in English I'll take. Okay, clear? Okay, great then. So if things are clear, we will close for today's session. So thank you all. So we have successfully finished 4 lectures of this Abhyas series. Still we have 6 more lectures. Okay, so 5 more lectures we'll spend on individual topics, and the last lecture on 16th is on complete fluid mechanics. We will have a quick revision on all the things, and we will solve questions from each and every chapter that we dealt with. Okay, so till now we finished 5 chapters: fluid and its properties, pressure and its measurement, hydrostatic forces on surfaces, and buoyancy and flotation as the 4th chapter, and differential analysis of fluid systems. So these are the 5 chapters that we have cleared so far, and I hope definitely you might have seen some new questions, some unsolved questions in very good textbooks getting solved in this class. Clear? So please type in the chat box, are you all finding this lectures very useful and finding some nice questions in this? Okay, so I hope in today's session you have cleared some good concepts about this stream functions, velocity potential functions, polar coordinates, Cartesian coordinates. Okay, then we came to the conservation equations. Okay, we talked about conservation equations, how to calculate discharge when velocity profile is changing. We came to a good discussion about all these points. Clear? So I hope this helped as a quick revision for you all. Okay, and whenever I could give you some short points, I've given linear strain rates, shear strain rates. Okay, so all these things will be definitely useful for you in the upcoming GATE examination. Okay, and mechanical, civil and XE aspirants can also attend this course, so that it will be a boost to all of you guys. Even chemical, if you are having some fluid mechanics, you can take part in this. Okay, yeah, sure. So shall we close this session now? So please type in the chat box. Thank you all, so much love. Thank you all. Fine then, if things are fine, we'll close this session for today. Okay. Okay then, thank you all. We'll again meet tomorrow at 11 AM with the questions on control volume analysis of fluid systems. Okay, so we'll see Bernoulli equations. Okay, we'll see linear momentum equations, angular momentum equations. We'll solve some questions on lawn sprinkler, all these questions with very easy understandings. Clear? Like in today's case. Fine. So don't miss tomorrow's session because many of you will be complaining about it. Okay. So in linear momentum, why this is positive, why this is negative, why this pressure is not taken. All these questions you'll get answers in tomorrow's session. So please don't miss tomorrow's sessions. Clear? Thank you. And next today have thermodynamics from Negi sir again in the evening. So in the afternoon after lunch hopefully. So please attend that as well. Okay. So this thermofluid combination and night Sandeep Chandrakar sir. So this thermofluid combination will definitely give a good click. Okay. Fine then. Thank you all. We'll meet tomorrow at 11 a.m. Thank you all. Bye. I'm signing off. So thank you all. I hope things are clear. Okay. Clear? So I'm putting off now. Thank you all. Thank you.